Welcome to my channel. This is the next session power system analysis. Today, in this session, let us see how to draw the reactance diagram for the provided single line diagram. So already we have discussed the same problem and another case of problem we are today going to discuss. The given question is draw the reactance diagram for the power system, neglect the reactance and use a base of 100 MVA to 220 kilovolt in a 50 ohm line. The ratings of the generator and transformer are shown. So this is the single line diagram and we have provided with an base of 100 MVA 220 kilovolt and this is used for the 50 ohm line. Okay, and in the coming to the single line diagram, it consists of a generator, transformer, transmission line and the transformer T2 and another one is the motor. Consider this as a synchronous. So here its own MVA rating and kVA rating and the reactance values are given, and similarly the transformer, transmission line, transformer T2 and for the motor. So usually while calculating the per unit calculation, there are three steps. First, we need to select the base MPa and the kV value. Here in the problem itself, it is given that use a base of 100 MVA and 220 kilovolt. So we are supposed to use the base for this in a 50 line ohm. It is specifically given use this for the 50 ohm line. Okay. So in the single line diagram, after selecting the base MVA and the kV value, we need to sectionalize. In the single line diagram, there are two transformers T1, T2 and if you sectionalize, there will be an 1 kV value still the transformer T1 and still T2 there will be another kV value and after T2 there will be another kV value. While sectionalizing, we come to know that three different kV values are there and the kV value for the transmission line is given as 220 kilo. Right? The step number one is choosing the base MVA value and the kV value, and step two is sectionalizing. Why we need to sectionalize? Because transformer voltages tends to changes and the voltage changes caused due to its transformation ratio proportions. Okay, so due to this we are going to calculate different kV values apart from the component transformer. Right, here in the single line diagram there is only two transformers. If there is the 3 or 4 or 5 transformers, the kV value changes depending upon the voltage proportions of the transformer. Right, consider here the all the elements of the three phase elements. Since it is not given, you consider this and proceed to the problem. Let us proceed the problem. Once again I repeat it. This is the single line diagram. For this single line diagram, we are supposed to calculate the per unit value calculation. The reason for calculating the per unit value is the system complexity is reduced. Okay. And as per the problem, I am choosing the base of 100 MVA at 220 kilovolt. This choosing is especially provided for the transmission line. Right? So once we know this, we can able to calculate the base impedance of the transmission line. This is for the transmission line. Base impedance of transmission line. The base impedance of transmission line is given by the formula kV nu square by MV nu. So the kV nu we chosen is nothing but 220 kilovolt and MVA nu is 100 MVA. kV nu is equal to 220 the whole square divided by 100. I get the base impedance of 484 ohm. The problem which we have already discussed, we have started from the generator. If some of the viewers who have not seen that, you just go through that and come to this case. We have already started with from the generator, since especially there is no MBA value or with a KB value base value is given, so we have started from the generator. Here especially the MBA value and KB value is given for the transmission line, and we are starting the case from the transmission line. For that we have to calculating the base impedance initially. And calculation of the base impedance, the actual formula for per unit is nothing but per unit is equal to actual impedance by the base impedance. Actual impedance, we know that it is nothing but the 50, and we need the base impedance, so we are calculating the base impedance by this formula, right? And the base impedance is equal to given by the formula kV nu square by MVA nu. Okay. And next we need to calculate the per unit for the transmission line. The per unit for the transmission line is given by the formula actual divided by the base, and the actual value is 50 ohm, and base which we have calculated is 484 ohm. I get the per unit value as 0.1033 per unit. Okay. And we have initially started with the transmission line, since it is given us the base and MVA and KV for the transmission line. In this case, the next component is transformer T1. We have completed this transmission line and we got one per unit value. The next is transformer T1, right? And for that transformer T1, we need to calculate the per unit, and its given values are 40 MVA, 33 bar, 220 kV. Since there is a transformer, we need to calculate another kilovolt voltage, because there will be a voltage change due to the transformer voltage ratio proportions, right? So we need to calculate the new kV value, and then we need to calculate the per unit value. And if we calculate the new kV value, the formula for calculating the new kV value is base kV on LT side, that is low tension side, is equal to base kV on HT side into LT rating divided by the HT rating. The LT rating and HT rating are given in the problem as 33 by 220 kilovolt. So I am taking this as the low tension voltage and this is the high tension voltage, and substituting I get the base kVA value as 33 kilovolt. And our aim is to calculate the per unit value for the transformer. Per unit value is equal to X per unit volt into kV volt by kV nu the whole square into MVA base nu by MVA base volt. It is equal to X per unit is equal to 0.15 into the old value of kV is nothing but 33. It is given in the problem as 33 bar 220. I consider this value as the old value. It is given in the problem as 33 by 220 volt kilovolt. I consider this 33 value as the old value, right? And the calculated new value is also 33. It is calculated above, so I substitute 33 by 33 into 100 by 40, which is equal to this per unit. Similarly, and the next component in the single line diagram is generator. Apart from the transformer, it is generator. You can see in this single line diagram, it is transformer T1, transmission line, transformer T1, and the generator. Since we have calculated here a new kV value for the transformer, there is no any other transformer. There will not be change in the voltage value, which is all passing towards the generator. So we can use the same kilovolt value for the generator. And while calculating for the generator, the X per unit nu is equal to X per unit volt kV volt by kV nu square into MVA nu by MVA base volt. And by substituting, I get the per unit value as this. Okay, and we have calculated values for per unit values for the three components for the transmission line, transformer, and the generator, and the leftover components are transformer T2 and the synchronous motor. And before going for the transformer T2 and the synchronous motor, we are once again supposed to calculate the base kVA. So coming to the single line diagram, once again the single line diagram. Here, apart from the transmission line, there is another T2 transformer. This T2 transformer tends to cause an voltage change, and this due to this voltage change, we are once again calculating the kV value. And the formula for calculating the kV value is base kV on HT side into LT voltage rating divided by HT voltage rating. In the transformer, the voltage proportions are given as 11 bar 220 kV. So I am taking the low voltage as 11 and high voltage is 220 and obtaining the voltage is 11 kilovolt. Substituting this, I get the per unit value was 0.5 per unit, right? And for the per unit calculation, we are using this formula in all the cases. We are supposed to use this formula especially whenever there is a change in the old value and the new value of the kV or MVA. If not, multiply the values given per unit values in means of MVA divided by kV square. If there is any no change in the case of kV MVA or no kV value, right? And next, the synchronous motor. The synchronous motor per unit value is given by 0.6 per unit, right? Our almost aim is to draw the reactance diagram. The reactance diagram for this provided problem is given by, we have a single line diagram as it consists of an generator. Generator usually it is represented by G1 in series with the reactance, and the transformer reactance, and the transmission line, and next another transformer, and the motor is given by EM1, or it may be denoted as EB1 since it consists of a back EMF. So in series with the reactance. Initially this is grounded. Okay, so XG1, this is XT1, transmission line XTL, XT2, and XM1. The motor is this. And the values for transformer T1, T2, T3, transformer T1, T2 are substituted thereafter. And for the transmission line, I get the value was 0.1033, and for the transformer T1 it is nothing but 0.3705, and for the generator 0.287. Similarly substitute for the transformer T2 and for the motor M. Okay, this is the reactance diagram for the provided single line diagram. In the question, it is given as the reactance diagram. If the question is asked as the impedance diagram, it is also similar. Instead of X, you get the value as Z. Okay, and the formula for that is nothing but Z per unit is into kVB node instead of X. Wherever there is X, you need to replace the X into Z. You are able to calculate the Z per unit calculation. Okay. If you like this channel, like, share, and subscribe. Thank you.